knowledge ni mo pè é. So, and kí ni knowledge nípa fixed point and optimization theory. Lọ́jọ́ yẹn a sọ̀rọ̀ nípa àwọn optimization problems.
Then,
So lára wọn, mo làwọn mẹ́ta tó wà níbí. Yeah, so these three. So, and their names as bó ṣe wà lójú screen yẹn. Okay. So the first problem is what we call the equilibrium problem.
yeah.
The second is the variational inequality rather.
Mhm.
Yeah, and the last one there is variational
Inclusion.
inclusion.
Minimization problem.
There are,
Ní
yeah,
ṣẹ́gbọ́.
kò sí nínú àwọn tó wà níbí.
Okay, bẹ́ẹ̀ni.
So mo sọ pé lára àwọn tó ń jẹ́ optimization problems ilé táwọn èèyàn ṣiṣẹ́ lórí ẹ̀ jù
Okay, mẹ́tẹ̀ẹ̀ta yẹn.
òun ni mẹ́tẹ̀ẹ̀ta.
Okay.
Yeah, and of recent gan ilé tó receive bóyá láàrin àwa ò tá a mọ̀ra wa
Okay.
this one second one yìí variational inequality
Dr.
òun
Aluko
là ń
ní
ṣe jù.
Dr. Aluko ń kí yín ó dàbí máìkì wọn yàn òṣìṣẹ́ bẹ̀ tí wọ́n ń gbọ́n tà ń sọ.
Mo ti rí mẹ́sẹ̀gì wọn. So recently ilé là ń ṣe. And the thing is, we've not mentioned species, but there are several abstract species táwọn èèyàn ti ń ṣiṣẹ́, and majorly ibi tẹ́ ti rí tíṣẹ́ ti ń jáde jù àbí táwọn èèyàn kọ pépà lè lójú is Hilbert species. So àwọn extension àwọn methods yìí àbí àwọn problems yìí, well, by default the problems have been extended to all the species.
Okay.
Whether it's Hilbert, because by default we don't remember is the Euclidean species.
Yeah.
So let me try to write now. So Hilbert species, we fẹ́ list àwọn species ní bó ṣe wà, so that ká tún tètè kọ́ yẹn lẹ́nu ìránsìn.
But currently báyìí a ti mọ àwọn optimization problems yẹn àtàwọn associated iterative methods tó lè solve wọn.
Mo fẹ́ ẹ mọ̀ pé Dr. Aluko sí ń bẹ̀ láti bẹ̀rẹ̀.
Bẹ́ẹ̀ni.
So àbáwọn náà ti go through àwọn tá a ṣe tẹ́lẹ̀.
Mo send the video yẹn sí wọn, then àwọn náà ní.
Okay then. So àwọn species yẹn.
Okay.
Agbára pẹ̀lú Euclidean species.
Rn.
Yeah. Then Hilbert species. Then the Banach space. So both of these are normed spaces. In fact, with this one, norm space, though most times absolute value for R, but what's in the n for n equals to 1. If n is greater than or equal to 1, then you're speaking about this as well.
Norm.
So for R, that is when n is equal to 1. It's absolute value. Yeah. But the moment n is greater than or equal to 1 for this, it becomes a norm space. Then after that, you see same people work Hadamard species, so which includes the card 0 species. So Amy of recent, I've never worked here, but in Israel, just before I went to Israel, I started working on this. Hadamard manifold. So to date, to publish some papers in space. So what happens is that if a method is used here, there can be an extension of such to this or to this, or to the other ones. So extensions, some spaces, all constitute new works because the spaces do not have the same geometry. They do not have the same geometry. Even though there are inequalities, Toba was satisfied here, it's satisfied here as well. So there are some of them like that. And there are some things we call analogs. Analogs. For instance, an inequality here, there is this inequality that we know for every norm space.
Triangular inequalities. It's triangular inequalities.
X squared plus 2 x comma y plus y squared. So, eléyìí hold for our norm space. So, nínú Banach space, it's not direct like this. It depends on the type of Banach space. Because Banach space is not only type. There's 2 uniformly smooth. There's uniformly convex. There's uniformly smooth. There's reflexive. So, one go from another got to me. Banach space is not to me. Just like I said, 2 uniformly smooth. Wow. Uniformly smooth gangan fúnra rẹ̀ náà wà. Ẹ pé gbogbo wọn ní geometry tó yàtọ̀ síra wọn. Then there's uniformly convex. But àwọn eléyìí méjèèjì they are twin báyọ̀ kí n pè ní twin spaces ni. Tí for instance tí AE bá jẹ́ uniformly smooth space. Tó bá jẹ́ E tó bá jẹ́ uniformly smooth space. The dual space of this will be uniformly convex and vice versa. Like really why uniformly convex. If E is uniformly convex, then its dual will be uniformly smooth. So I want a dual twin relationship now. I don't know what to call it now. So but they have that kind of relationship. Then after that, there's still what we call the reflexive Banach space. Reflexive Banach space. And these spaces, the metric that is defined on them is different. And we're saying they define, though all of them, there are norms in all of them, but majorly here, we use what we call the Bregman distance. Bregman distance, which is defined as this x squared plus f of x minus f of y plus grad of y comma y minus something like that. So definition, I think plus. So that, and in uniformly smooth, that's what we call the Lyapunov function. Lyapunov function. So so, but these are just about the species.
Okay.
Species. So we go back to the problems. So we have said there are, here we have mentioned 3 here.
Three major
the equilibrium
problems.
problem, the variational inequality, and variational inclusion problems. So these are just some of the optimization problems that are solved in our species. Our species that's Darupan. Okay. So, and in these problems, we have said that in one F here, F10 we use, let's call it bifunction. And in 2 is just 2 and 3, they're just nonlinear operators. You can call it function, you can call it mapping, so whichever one you're satisfied with. And they satisfy different monotonicity conditions. We define monotonicity condition here the last time too. I remember there are several monotonicity conditions. So, but a majorly full equilibrium problem that people have solved is either monotone or pseudo-monotone. In fact, I'm recently considering solving some of the problems in motivation PhD to the monotone. We talk about that one. So maybe it about progressing, so we can share those problems among ourselves and then
Sorry,
solve it differently.
Balẹ̀. Mo ṣe bí
Now,
fún VIP náà, ṣe ń pé ó dàbá ní fún iteration rẹ̀ náà, ṣe ń pé ẹni he ń bẹ̀ so tó bá wà strongly monotone. So mi pé strongly monotone nìyẹn fún bí projected gradient kí ló ń pè method. Tí mo sọ sí ṣe pé ní fún f yẹn fún bifunction ó gbọ́dọ̀ wà either monotone àbí pseudo monotone. Maybe fún VIP
fún equilibrium problem nìyẹn. Fún equilibrium problem. So for the bifunction f can either be monotone or pseudo-monotone.
Okay.
As for A, there are several monotonicity conditions that have been studied by authors in the literature. They include, but not limited to, inverse strongly monotone, monotone, strongly pseudo-monotone, quasi-monotone. All these monotonicity conditions have been studied for two. Variational inequality. Yeah. And from 3, majorly in Cotemari, myself is just monotone.
Okay.
So, and monotone last time only include this inverse strongly monotone, only include strongly monotone, only include which other one? Maximum monotone is always there too. That's another condition. So maximum monotone. So for inclusion problem, normal problem, the normal linear problem, none. What is that linear problem? We solve I'm at several times I'm going to show around problem like ax equals to 0. Where is a constraint? Maybe, for instance, 2x plus 5 equals 0, for instance. So you rule and you run with it.
Okay.
I think we call this the kernel of a function. And when solutions to satisfy in kind, they call it kernel. That I should run with it in year 3 or year 4 mathematics. So they call anything like that, yeah, kernel. So but like now this is just for a single valued mapping. Single value. Yeah, single valued mapping. So maybe T going from X to X. But the moment this thing is no more single valued, maybe it's now point to set, something like this, to the power of X. So if T is this, then we will not call it this type of problem again. This 0 problem changes now to 0 in TX. The mapping is T now. 0 in TX. This same problem, when AX equals 0, which we are changing. No, this is only when, now this should be T because we're using T. So this is when it is single valued and when it is multi-valued. So this, again, you call it this point to point, but this is point to set. Quickly, power set, Lily, Abi?
Ben.
Abi?
Ben.
Oh, yes.
Yeah, so this is point to set, Lily, or multi-valued. Some of those things say, okay, another word that only if you do single value mapping.
Correct.
It's called point to point. Point to point, so single valued. Single valued. Then point to set. Multi-valued. Is that okay?
Yeah.
So okay, so now, sir?
Okay, I just want to confirm if the speaker is working.
Ó ti ń ṣiṣẹ́, mo ti gbóyin lẹ́ẹ̀kan.
Okay.
A kú ọjọ́ mẹ́ta.
Yes, sir.
I think going by dọ́kì.
All right. Thank you.
So, now, a ti discuss àwọn problem yẹn báyìí, àbí? Then, the next thing is fixed point gangan. So, tí doctor bá ti wo fídíò tá a send nígbà yẹn, a ti try láti relate kí ni connection tó wà láàárín fixed point àtàwọn problem tá a solve ni. So, what we're doing basically is using fixed point methods láti solve àwọn optimization method yẹn. Tá a list mẹ́ta sókè ni. So, and the several methods of those things, evolution and our method, at it discussed in the first class. Evolution and our method. So the first method is this peak iteration. So, and it was this iteration that was used by Banach then. So Banach principle in 1922, Loufoucault approximates the fixed points. And then fixed point equation, when you go to looking, this is what is called fixed point equation. And I tried that so if a map is defined by 3x plus 5, fixed point imagine, is just make this 3x plus 5, just replace this tx here now by this guy and solve for x. So fixed point 10, yeah. That will approximate our values here. On the Picard, on the Banach should define iterative method here. Talk with Picard iteration. So this sequence of iterates will approximate that fixed point of the mapping once the mapping is contraction. And what it is for a mapping to be a contraction, I define it. So it will be a contraction if it satisfies, let's say we're using an arbitrary metric now, tx, ty.
Tx, ty
is less than or equal to k kd of x, y. To display, I don't know. X, y, where k is a value in 0, 1. So any map to satisfy, this is just an arbitrary metric. But me only norm, only absolute value. So whatever metric it is. So any map to satisfy condition. That's what is called a contraction mapping. And so he approximated the fixed point of that mapping. When you approximate most of, they are non-linear problems. So non-linear problems are a direct solution. So they have approximate solutions.
Exact solution.
So sometimes the value solve a marine so changes see approximate. So but I want me to by solving Walino. So there's nothing wrong. If the title of the article is iterative method for approximating solutions to iterative method for solving. So those are our so and we started the evolution of methods for solving deviation inequality, but before then, continue. So this was the first method. Then after that, LOMI, because this method only approximates contractive mappings. And in practice, our constraints mappings here were restricted to contraction. They have other properties. Least after contraction is the non-expansive. These are another property. So to approximate that, Picard iteration couldn't do it. The Krasnostersky were introducing the Krasnostersky method. And this, from what I mentioned the last time, is that this sequence of iterates is generated by a line segment joining xn and txn. So it's a line segment joining or a converse combination, exactly, a converse combination of xn and txn. So either two of those, you can call it a converse combination of xn and txn, or you say it's a line segment, or xn plus 1 is a line segment joining xn and txn. Notice that alpha is a constant in 0, 1. Alpha is a constant in 0, 1. And if you look at that constant, the addition of both will always give you 1 at any point, because 1 minus alpha plus alpha is what? Is 1. one. So then man will not generalize that method. So he replaced the constant alpha in the Krasnodębski method by what? By a sequence. So by sequence. So and to prove the convergence, set conditions with alpha here. So it's not just alpha, so it sets condition on it, so that you have to find out in papers. Because of that, we're not going to dwell on the conditions. We don't have time for conditions. So on Lorota, it is known that the Picard, Krasnodębski, and Marr methods only give a weak convergence. However, the moment you move from the Euclidean space, in Euclidean space or finite dimensional space, the notion of strong convergence and weak convergence, they are the same. Because you can't separate both once you are in a finite dimensional space. But the moment you move to infinite dimensional, then you have to give us a method, or you have to propose a method that is strong convergence. So more strong convergence is more desirable in case when the space is not finite dimensional. So to do that, the very first method that was introduced to solve this, or to prove strong convergence, is the Ogazu method, and it's generated by the sequence given here. If you look at it very well, it's a combination of the Picard iteration and this is a now, but this P here is a projection of this value here of this sequence onto Cn. So it's a projection of Yn onto Cn. Cn being a convex set. So Cn is a convex set. So it's the easiest to prove when we are solving optimization problem. Method automatic define by normal easy to prove you. But most times because projection in last it's a problem on its own. So projection is a problem in case or in situations where this Cn is complex. Like quite simple Cn or easily the formula of calculate projection. But if it's complex, it's a problem on its own. So the method will not be as effective as we want it to be. So I think it's the same thing here. We've repeated the same thing. Now, instead of it being only Cn here, you can see it's only one convex net here. This is another one here. This is an intersection, another problem. So though there's a man called von Neumann. Von Neumann prove if you're looking for the projection of a point onto intersection of two sets, so we can calculate that by composing the composition, by having composition of the different projections. For instance, P of C intersection Q, projection of X naught on this. So we calculate it by saying P C. And we projection time say map no. So I compose y. This also these values are almost the same thing. This is a map. See, so you know that it's going to give you a value. So it gives you a point. So the projection, let's say for instance, goes from element of H onto C. So and most times, if the element that you're projecting onto is in C, the element I've projected onto is in C. So it will be, don't put any projection saying is the nearest point. They call it the nearest point mapping. Nearest point mapping. The new Euclidean space on orthogonal projection, nearest point mapping. So one point to sum element conjugate. That's what it seeks. So one element to sum ju. That I might read in further mathematics and I shall go to job there. So So also calculate by this also gives an approximate. So it's not directly that they're equal. So you can approximate this problem using this. So first, I will project onto the point. Then our alien value this will be a value in Q. Then whatever value that is, we now project Q, the element of Q, onto C. So that's another way of doing that. Only another way of solving this problem here. So, but see, I'm working here. It's a convex set and budget problem now. You're individually that you're projecting onto. That's another problem itself. So that this here, the CQ algorithm language. So they said the execution of CQ algorithm is known to be slow or difficult depending on the convex sets. So let's avoid drawback here that is being slow of the algorithm. Then they introduced this guy in 1961 or thereabouts, I think. Yeah. So in 1961, we introduced this Harper method. Harper method, you can see that it's also a convex combination, Abi. So it's also a convex combination. It's a segment as well because it connects our points by looking at this number alpha n and 1 minus alpha n. This sum one 1. So you call it a convex combination or you call it a line segment. So it joins alpha n. It joins u. This u here is a vector, and this is just a sequence. Okay. So it joins that, and this is non-linear mapping. So this method, anytime to join a convex combination of a vector and a sequence like this, that is called the Harper method. And most times, anybody strong convergence, add line because he wants the sequence to generate, he wants the sequence is going to generate to be strong convergent. So we want to see some of those. So this is another one. And this one now is called viscosity method. So this method is called viscosity, and also a convex combination of, now this now is now two sequences. This is a sequence here, and the other one here is also another sequence. But this sequence here is always a sequence that is generated with a map that is contractive. It's generated by a map that is contractive. Where T approximate Lele. But this guy here is a nonlinear mapping, which is contractive. So this is always contractive. This is the mapping we want to approximate, just like it is the mapping we want to approximate here. Mapping you have to approximate. You want to get the fixed point of this mapping here. And the mapping is what? Non-expansive. But here, instead of it being U, as in the case of Harper, it is now a sequence that is generated with what? With the contractive mapping. So those are strong convergence methods. So I want here definition to try to give me. This is the contraction mapping, and then in this case, it's not a metric. It's not an arbitrary metric. The metric here is known, which is the norm. So this is a contraction, and this is non-expansive. You can see the difference. There is no constant there. The constant there is now like 1. So the constant there is 1. So this is non-expansive. I think we do have other one. No, allow me. So this here, this is called the Ishikawa method, and the Ishikawa method is a combination of two man. This is man, this is another man. So man meji, no Ishikawa method. And you see, this is a converse combination of xn and txn, and here is now xn and tyn. That is, this value here are composed equality. So we use this method again to approximate a fixed point of t, and this also will give you a weak convergence, because see method to move strong convergence one. But here, if you look at this other one here, the first one is man and the second one is Harper. So this is Harper because this is this U here is a vector and this is a sequence. So this combination will give you a strong convergent algorithm. So this is a strong convergent algorithm. The first one, the former, is not strong convergent. So this is another combination man happen. Eléyìí náà máa fún wa ní strong convergence. And this one, shall identify àwọn eléyìí. Shall identify mẹ́tẹ̀ẹ̀ta.
Picard iteration ni tìyẹn.
Picard,
Kejì man.
man, àti happen.
So this is Picard here. This is Picard. This is man. This is happen. So both of them, méjèèjì yìí máa fún wa ní kíni o, strong convergence because of this happen here. So both of them will give us that. So ẹ rí nǹkan tí mo sọ lẹ́ẹ̀kan pẹ̀lú zero problem.
Yeah.
Yes.
So this A here, will it be point to point or point to set?
Point to point.
Point to point. Ibẹ̀lẹ̀ ti lè rí equal to. But tó bá jẹ́ pé inclusion, so that will be point to set. Point to set. That is 0 is in, instead of 0 is equal to AX. So 0 is in that subset. Okay, AX, am I just subset? You're going from T to, okay, let me use A now. Tomorrow T again. Because A lower man. So I'm going to use A. In fact, to separate again. So A from X to X. So this is point to point. Then that is the zero problem. 0 equals to X. But the moment is A from X to 2 to the power of X. Àwọn nǹkan tá a máa rí bí, àwọn tó máa wà bí, they will be sets. Àti ẹ̀rí nǹkan kan mi, a gbọ́dọ̀ rí X àti eléyìí. Méjèèjì yẹn sure, àbí?
Empty set àti set yẹn for now.
Those ones are subsets. Èmi náà ti ń kọ́ math with Lugaf díẹ̀ ni. So this one are there. So ó mì pé anything tẹ́ bá ibi tá a ti ń wá nínú zero tá à ń wá sí, à ń wá nínú kíni o, à ń wá nínú set ni. So 0 in AX. So 0 in AX. So this is inclusion. Both of them are zero problems, but this one can be separated. It's what? Inclusion. So, but sometimes, just like I mentioned something, I'm sure. Sometimes only J 0 in A plus B. 0 in A plus B. Instead of A last one, as you say, was A plus B. You come point to point, single valued. Maxima. So this maxima is always point to set, that is multivalued. So now gbogbo àwọn method tá a wá describe lókè yẹn ṣe rí pé nígbà tá à ń dárúkọ tá à ń sọ pé method gbogbo method yẹn kí ni la fi wọ́n solve inclusion problem kí ni ìmọ̀ àti hangi kẹ.
Ẹ mú arrow-down yẹn wò náà sà.
Arrow-down. Mi ò rán ní kíní tó ń bá mi ṣe escape nǹkan. Kí ni mo lè ṣe escape? Okay, escape lónà. Escape.
What of this X? X is the one in your right side.
Ṣé o mo ti tẹ ẹ ó ń rẹ ó sọ. Gbogbo method. Sá?
Wọ́n ní àgbo ní tán lórílẹ̀ o.
Okay. Mo ti kíní ẹ̀ mo ti tẹ̀ tẹ́lẹ̀ bóyá ọwọ́ mi ò wá tẹ̀ dáadáa ni mo ti tẹ̀ tẹ́lẹ̀. So ṣe rí gbogbo method tá a describe yẹn tá a sọ pé a fi ń solve ẹ rí pé gbogbo ẹ̀ kíní là ń sọ sìn fixed point gbogbo b tí tẹ̀ ń wọ ìsìn fixed point ni a lè lo gbogbo method yìí náà láti fi solve àwọn problem yẹn gbogbo problem ẹ̀ tẹ̀ tata ti dárúkọ lókè yẹn. So and how kí náà fi wà related ni pé ẹ wo rule for instance sin note that the resolvent of A defined by resolvent defined, though it's not for this one. Error this resolvent is for a maximal monotone operator only resolvent. So this should be 0 in AX instead of AX equals to 0. So 0 in AX for maximal monotone resolvent by. So note that the resolvent of A defined by this, note again when A is what? Maximum monotone, is firmly non-expansive, which is non-expansive. That's the line. Only property who are firmly non-expansive. And firmly non-expansive mappings are non-expansive. Since the classical method that describes okay, a lè lo fún non-expansive. Ó mean wípé a lè fi àwọn method yẹn náà solve kíni o, zero problem. So nǹkan tí mo sọ ṣe get it right.
Okay.
So, and for instance, ẹ wo irú eléyìí sin combination man àti happen yìí sin. So, eléyìí sin man sin kò tẹ̀ tún solve problem kan. Irú method that I introduce in sin problem méjì ni ó approximate. Ó máa approximate fixed point eléyìí. Á dẹ̀ approximate zero eléyìí náà.
Okay.
So, this is exactly the same thing pẹ̀lú nǹkan tó wà níbí, this first one tá a sọ níbí.
Ben.
In ohun àtẹlé nǹkan kan náà ni. Method tó wà ń sálẹ̀ nísìn tí mo kúrò lórí ẹ̀ àtẹlé the same thing. The only difference is now, a ti change t yìí nísìn. A ti sọ di kíni o. A ti sọ di resolvent zero problem. A sọ di resolvent zero problem. Kí ló dé tá a definition ni pé kíni o. Tí tó wà níbi tó kíni is non-expansive. Eléyìí náà wà kíni o. Ó náà wà non-expansive. So this method will solve a common solution to these two problems. And if I were to write kékeré yẹn sìn, a o paper yẹn kan nìyẹn. Téèyàn kan ti jọra fi kọ paper kan ní time kan. Ọ̀sẹ̀ yẹn gbọ́dọ̀ tún kọ́ lórí eléyìí sìn báyìí wọ́n ti kọ́ sẹ́yìn o. So paper kan lẹ́ra ń wò yẹn. Eléyìí tán tẹ̀lé náà. In fact, a ṣe comparison mi ò mọ tí mo tún lọ sókè fún gan náà lélẹ̀. Ẹ rí pé tó ní tí tó approximate fixed points lásán eléyìí. Now, this is not a combination of both. Just that this T, the second T here, actually replaced by Kinu, the resolvent of a zero problem. So clear?
Yes, yes.
So, mi ò ní fẹ́ ká lọ sínú split feasibility problem lẹ́ni. I stop see your description of these methods now. I stop seeing your description of methods. I'll fẹ́ padà lọ sí variational inequality. Let's have maybe 5 more minutes. Ká padà lọ sínú variational inequality. Nǹkan tá a ti sọnù variational inequality tí mo bá rántí tẹ́yìn náà bá dé gbàgbé. Àkọ́kọ́ sọ pé 1, variational inequality is described by this. Find x in C.
Inner product of A.
Such that the inner product of AX, YX is greater than or equal to 0 for all Y in C. So any X to be satisfying can only solution of variational inequality. Any X to be satisfying can only solution of variational inequality.
No.
So Emma Bino Mompanion. So only solution of variational inequality. Add to explore relationship to Gagoni pẹ̀lú fixed points. Lọ́jọ́ yẹn àbí?
Ben.
A sọ pé X kan máa jẹ́ solution problem yìí. Tó wá pé X yẹn lè solve variational, ó lè solve fixed point problem yìí. X equals PC into X minus lambda AX. Or kẹ̀pẹ̀ ní PC into I
minus lambda A.
Minus lambda A X. So, tẹ́ bá compare ilé pẹ̀lú fixed point problem yẹn. That is X equals TX. Ó mean pé T and replace T by PC
into 1 minus
I minus lambda A. Kò ṣe wọ́n o, I know identity mapping. So now, ẹ wá wo irú method aláwọ̀kọ́, the Picard iteration, xn plus 1. kí la sọ pé ó jẹ́
tx
xn àbí ẹ replace t yẹn again by this value ó mìíràn pé láti solve relational equality ẹ lè lo method pc into
I minus lambda
I minus lambda a xn ṣe rí method tẹ̀ wò yìí
projected
Hmm?
gradient method.
òun náà ń pè ní projected gradient method projected gradient so that describe àbí pé láti solve minimization problem o method tán lò láti solve minimization problem òun gan náà is a method generated by this equals to xn minus lambda gradient of f xn. Tẹ́ bá wò ó, ilé àti ilé ìfẹ́ jọra wọn ní tó wà nínú yìí cause ẹ lè kọ ilé náà báyìí as I minus grad of f okay ẹ jẹ́ ká fi lambda sóhun náà lambda n yẹn wọ́n ń pè ní step length òun náà ní iṣẹ́ tó náà ṣe bẹ̀ that xn so tẹ́ bá fi compare ilé ẹ máa rí pé òun àti ilé ìjọra wọn àbí bí ìgbà pé èèyàn kan replace a where a is now what kí ni a jẹ́ ń bẹ̀ wáyé grad of f
Grad.
àbí.
Yes.
So, but the only difference between this and this is that eléyìí ní kíni o, only projection mapping. Check it.
Projection.
So the only thing tá à ń rí inú ilé à ń rí I identity a lè rí gradient nǹkan ń bí but ibi I A and what and PC àwọn maps tó wà ń bẹ nìyẹn map méjì péré ló wà nílé I and grad I and A. So A àti grad yìí they are playing a same role so la ṣe ń pè léyìí ní kíni o projected gradient. A sọ pé projected gradient yìí just like that kí lorúkọ ẹ̀ Picard hydration sẹ́wọ̀n pé Picard hydration kò lè solve ju non contraction lọ àbí kò lè solve ju contraction lọ so eléyìí náà òun náà ò lè solve ju strongly monotone lọ projected gradient yìí kò lè solve ju kíni o when A is strongly monotone. But mo sọ nǹkan kan lọ́jọ́ yẹn sẹ́yìn rántí nǹkan tí mo sọ lọ́jọ́ yẹn.
Ẹni àwọn other monotonicity yóò mọ jẹ́ extra gradient.
Ìyẹn gangan mo ń sọ ibi tí mo ń lọ kọ́ nìyẹn ibi tí mo ń lọ ni pé mo sọ wípé àwọn èèyàn kan ti explore this same method láti fi solve monotonicity tó weak ju eléyìí lọ tó weak ju strong lọ.
Okay.
Mo sọ nǹkan yẹn lọ́jọ́ yẹn pé mi náà try láti explore ẹ̀ fún nínú space mi though mi ò tí ì rí ṣe náà so strongly monotone a wá sọ wípé ìtorí pé eléyìí kọ́ ni the most in fact ẹ wo orúkọ ẹ̀ gan strong. So àwọn other application tá à ń sọ ẹ lè rí strongly monotone gẹ́gẹ́ bí contraction náà ẹ máa rí àwọn monotonicity condition tó weak àwọn constraint yẹn tó pé àwọn tó weak ju eléyìí lọ so for instance lára ẹ̀ ní monotone gan lásán monotone tó tẹ̀lé eléyìí so gradient yìí projected gradient yìí ò lè solve ẹ̀ nítorí ẹ̀ náà ṣe lo method tí wọ́n pe obìnrin kan ní Koplevich mo ti gbàgbé ọdún títí ẹ̀ o bí 1970 gangan ní Koplevich náà tí mo bá ṣe mistake àbí 1967 tí mo bá ṣe mistake òun kọ́kọ́ lo nǹkan yẹn fún nǹkan tó ń pè ní saddle point problem your more formulation lórí so I'm not going to describe that for you so you know lè lọ wá saddle point problem so ó lo nǹkan tó ń pè ní extra gradient now adaptation ẹ̀ sí kí lorúkọ ẹ̀ sí variational equality lè ní wá fẹ́ kọ́ ẹ̀ so method yẹn wà generated by yn equals mo kàn ń lo y ni ẹ lè lo nǹkan mi ò lè jẹ́ u o ó lè jẹ́ v o wọ́n pín gbàtẹ́ wáyé wọn pé olóòdù ti rẹ̀ gbẹ́ni àfi yn gbogbo gbà so xn minus lambda n a xn then xn plus 1 will now be xn plus 1 will now be pc of xn minus lambda n a yn
Extra gradient.
so this is extra kí ló dé tó fi jẹ́ extra gradient
Àti ní
a yẹn ti di méjì
gradient
a
kan.
yẹn ti di méjì gradient kan mi so tó náà ṣe pè ní extra gradient so ilé ìwárí àti fi ń solve àwọn other monotonicity condition tó weak ju eléyìí lọ so in fact ó solve quasi monotone náà. Ó solve quasi monotone. So but eléyìí náà tá à ń wò nísìn ó ń ṣe pé ṣe mọ̀ pé torí pé a ní issue pẹ̀lú pé ìyẹn ò lè solve nǹkan tó kéré sí strong loan tó weak sí strong loan tó bá ṣe bọ́ síbí kò ń ṣe àrùn nìkan tó ní nìyẹn o táwọn èèyàn ti explore lára àwọn àrùn tó ní ni pé Erlander n10 òun gan náà ẹ gbọ́dọ̀ choose ẹ̀ nínú kí lorúkọ nínú nẹ́ẹ̀tì yìí 1/L tí L yìí máa jẹ́ Lipschitz constant kìíní Lipschitz constant ṣẹ́ẹ̀dẹ̀ tún rí nígbà míì àwọn nonlinear mappings yẹn àwọn míì wà tó pé ẹ lè gẹ̀ẹ́tì ok woru map yìí sìn e raised to power x1 tí wọ́n bá define map báyìí sìn kí ni